just kind of knew we wanted to be a group. And so Jake came up with the idea of an automated greenhouse. And basically what we wanted to do with that, or the reason we chose it, is because we knew we wanted to solve a problem that affected everyday people. So we didn't necessarily want to do something in a manufacturing setting. The problem with this greenhouse solves is that obviously plants getting frost on it. Plants die in less than 10 minutes at 27 to 30 degrees and less than 5 hours at 32 degrees. And what people don't really understand is that the ground is actually colder than the air is. So that's why when you wake up in the morning, there's a bunch of water on the ground, because the ground is colder. So the greenhouse we have, at a certain temperature, it will close, and that prevents this water from getting onto the plants, which then prevents them from freezing, which ultimately in the end is why we chose that as our problem statement.
So I'm Jacob Jones. I'm a traditional option, and like Christian said, we wanted to go for more of a product rather than like a service project. So like our design philosophy was we wanted to incorporate a fully automated system that was able to retract and open to cover plants to prevent frost from getting on them. We also wanted to implement an override remote, so that way, say like the temperature was like supposed to be like 15 degrees, rather than using the temperature sensor, you know it's going to frost, you can open and close it on demand. So our design strategy, we started out with research and calculations. We spent a lot of time with Mr. Burden trying to do a lot of mechanical calculations with the torque of our motor, and to make sure it was going to be more than enough powerful to open and close our system. I also spent a lot of time with Dr. Prio, and he is a physics professor, and he also helped me with how our structure was designed on the point of torque and how much weight we are going to need to pull up and a lot of stuff like that. We also wanted to manage our expenses with $300 budget. That's not a lot, and before Dr. Jalali mentioned it, we never even thought of asking for more money since we didn't have a sponsor. So to manage $300, like you don't want to go over, and you want to make sure that's one thing for sure that you meet. Time management, we had a lot of time throughout the week set off that we were going to work on our project as a team. Very little aside from the programming was done like individually. A lot of it was a lot of brain power that we were coming up with for the idea of the structure and the wiring and how it was going to go. And then Aaron was our programmer for the system, and he spent a lot of time trying to figure out how the components were going to function all together. Lastly was work through our failures. We knew going into this it wasn't going to be perfect. It wasn't going to work the first time we did it. It wasn't going to work the second time we did it. But we didn't want to get discouraged, and we didn't want to just turn in something that say here it is. It's not really what we wanted to do, but it works. We wanted to come out at the end of this and have our product function how we wanted it to function.
My name is Christian Morales. I'm a traditional option. Our timeline shifted a lot throughout this process because we ran into several problems along the way, so things kept on getting pushed back. But we were able to meet our goals on time because we reserved a lot of time to finish everything. Originally, we wanted to get the whole project ready to test by Quest, and I think we completely got it working last week, and we were able to test it this past week. But with all the problems that we had, we definitely got pushed back a lot over time.
So this is our expense sheet. Like I said, for the $300 budget, we wanted to make sure we stayed underneath that, and we did. So our total with shipping, The total and the tax was $274.52. So we actually managed to stay underneath that by $25.48.
So after we decided what we wanted to do and how much money we had to spend, we had to decide who we wanted our customer to be. And obviously, whenever you're implementing something like this, you can't cover up 1,000 rows of a cornfield. So we ultimately decided to roll out large farmers, and we decided to focus on, you know, your hobby farmers, local produce, gardeners, things like that. So then after we decided or who our customer was going to be, we kind of wanted to go out and talk to those people and ultimately see what they wanted to have. So we all took a trip to Lowe's and we talked to the garden associate there, and we told her our basic design, and she said she liked everything about it, but she wanted us to add solar power in there. And at the expo we had a couple weeks ago, a lot of people also said that solar power would have been a good idea. Then Jake drove over to Dick Adgate, which is a local florist, and he talked to them, and he said something that he thinks the customers that he deals with would want to have is easy to operate and easy to move around. So obviously easy to operate because not everybody's an engineer, not everybody programs as good as Aaron does. So easy operation is key. And then mobility, you know, obviously you want it to be easy to set up. So then we also have some gardening experience, so we kind of took an introspective view and made some things that we also thought would be nice. So we made it durable, and if something broke, we wanted it to be easy to replace the parts. So after we came up with what we wanted to have, we came up with an initial concept, which is basically a pole cover style structure, which would cover like a 2-foot row of your garden, and it would cover the whole row. And then the reason we decided to go with this initially was because it could cover a large span of the garden, and you could connect, you know, 2 or 3 of these together on one motor, which would drive your costs down. Ultimately, initially, we also included solar power, but again, with a $300 budget, we decided that was out of scope, and for the final design, we decided to eliminate that.
Final concept, we've settled on the final concept, which is a dome-like structure that has the motor as a pivot axis, so it deploys based on the pivot. This was lower cost. We decided that we wanted to focus more on the electrical system, on the mechanical system, so we built the mechanical system as a proof of concept to show that it works. We want to be able to implement this system, the electrical system, to a bigger system like our initial design, but we couldn't because of constraints. We wanted it to open and close based on temperature, so at 40 degrees it will shut, and when it hits 45 degrees it opens back up. We also wanted to work on Wi-Fi, so you could connect with your phone or like a laptop so that you can manually force it open or close based on that. We also bought 2 Wi-Fi controllers, one as like a receiver and one as a transmitter, so that one could be attached to the device and then you could use a button on the other like a garage door remote to open it manually.
So these are our final sketches. As you can see in the top left picture, we had 5 support rods, and this support rod is actually the only one connected to the spinning axle. The other 3 are free floating on what we have is just a support structure. This is a top view of what our design actually looks like over there, and it's just to show that how it would cover the plants, how it would open and close. And then the bottom picture, that's our gear and our axle and the housing our electronics would be stored in. So we actually got the gear and the motor from a treadmill Christian had that was broke. So we took that motor and the gearing it already had and just made adjustments to it to fit our specifications.
So I'm Aaron Pfeiffer. I'm a digital option, and for this project we decided to go with an FPGA, which is a field programmable data array. the reason why we did this is because I was familiar with it and I wanted to learn more about it. And we also used the Wi-Fi controller. We were programmed in Arduino, which is C-based.
So for testing, we tested each main component of our system individually. So our sensors, we tested each component 20 times, and our sensors, the sensors we ordered, they were labeled as linear Hall effect sensors, and when we received them and read the spec sheet, they were actually a latch. So the problem with that is our magnet, when it would get in front of the sensor, would go high, and when it would go away, it would stay high. So what our Hall effect sensors were intended to do was when it was in front, it would go high, and then once the magnet moved on the pivoting support structure, it would go low, and then once it got in front of the other sensor, it would go high, allowing the FPGA to know the position of the poles. So that passed 14 out of 20 times. That's without adjusting the magnet. When the magnet was adjusted to the correct spot in front of the sensors, it worked every time. The temperature sensor we tested on the FPGA with a LED. So what we did with that was we got cold water and we just used air temperature, and Aaron had it set to where once it was like 10 degrees below air temperature, the LED would turn on, and once it was out and warmed up above to the threshold, it would turn off. And that passed 20 out of 20 times. The motor, it passed 18 out of 20 times, and the problem with that was the belt we were unable to tighten the belt tight enough by hand to have enough torque from the motor. So what we had to do, we had to implement a rod that actually tightened the belt, because on the treadmill there is a bolt that can be wrenched to pull the belt as tight as need be. And so it failed 2 times just based on motor slipping. And then the Wi-Fi is what we had the biggest issue with. With all the different electronics in the room when we were testing it, we had trouble connecting to the Wi-Fi module from the receiver. And so that actually only passed 12 out of 20 times. And here are some videos. So this first video, this is just us testing the sensors on the positioning, and we actually didn't have our motor powered up enough to work.
Yeah, we had it running at about 50%, and we had to up it to about 55 because we wanted to slam
So
open.
with sound, you can hear the motor when it turns on based on the frequency Aaron has it at. And then, that's not what we want. And then, when it gets in front of the other sensor, it closes, or it turns off. Next we have, this is our temperature sensor working. So what we did was, we have the temperature sensor submerged in cold water, and again, if we had sound, you'd be able to hear it.
Yeah, the temperature sensor takes a while to, well, not a while, it's just a few seconds, but it looks like a long time to adjust the temperature of the water.
And
so Jake starts playing with it. He doesn't realize it.
That's where our sensors were faulting us. The LED on the FPGA was working, so our temperature sensor should have been working. And here our magnet wasn't lined up with the sensor. But again, once the sensor was in proper alignment, it worked.
The same problem with the motor. We had our motor too weak when we were doing that because we didn't want to get hurt.
The last one
was only
yeah.
about 50%.
So this is where we have the temperature sensor out of the water, and we're waiting for the temperature to rise.
Aaron has his hand warming it up.
And then our last one, we actually powered our motor strong enough, and Aaron connected through his laptop and
Connected the Wi-Fi sensor to the laptop, and he just manually opens it.
and then it stops.
We also chose to only cover half of the enclosure because we felt that if we covered up all the way, we wouldn't be able to see our sensors and adjust them the way we needed to, and the plastic would just be in the way. So we just covered up halfway for concept. Mechanical issues, these are some things we ran into on the mechanical side when it came to building the greenhouse. They're not as important as the electrical issues, but I feel like they're worth mentioning. The pivot rods, we had 3 rods in the middle, and they're just supposed to float freely, and we weren't sure how we wanted to do this. So we spent at least 2 days coming up with ideas on how we wanted to do that, and we ended up using turnbuckles that let them move freely on a pivot point. We didn't account for how heavy the plastic would be, so when we ran our motor calculations, we ended up having to use more power than we expected. And then the big one was that the belt couldn't be tightened enough by hand, and we didn't account for this at all. So when we would run it, the belt would just slip and not catch. So we ended up having to put a bolt in that would butt up against the belt in order to make it tight enough. And then even at that, that was not tight enough and the motor would slip occasionally, which would cause errors. Electrical issues, there was quite a few of these. For our power supply, we originally wanted to use a 12-volt power supply that ran at 14 amps because once again, we didn't account for the weight of the plastic or the motor slipping. So this ended up not being powerful enough to flip the enclosure over, and we ended up switching to a 24-volt power supply that we were able to obtain. The sensors, Jake mentioned it earlier, but we ordered latch sensors instead of Hall effect sensors, and those wouldn't work. So we ended up having to use, there's actually a picture of the sensor right there. We ended up having to use analog sensors, which give you a reading of like, it always reads as being 1.9 volts, and then the closer the magnet gets to it, the voltage starts to steadily increase. So we ended up having a lot of problems because Aaron had to program a threshold that would put up a flag, and that threshold was very minimum. So he spent a lot of time trying to figure out the perfect threshold. In this picture, you can barely see it, but there's a sensor right there, and you can see the magnet, it's that cube, and the magnet wasn't very strong, and when sometimes the magnet would move and it wouldn't activate our sensors or trigger them. So the motor would just end up running continuously until we forcefully stopped it or moved the magnet to the right position. Jake once again mentioned the Wi-Fi module noise. When we were in the STEM showcase, there was several mobile devices and such around, and it prevented the Wi-Fi module from working as intended. The same thing ended up happening when we were testing it because we were in the school building.
So these are some general STEM showcase comments we wrote down when we were talking to people. It was just good. It was nice to get some positive feedback from a lot of the people walking around, and we actually had one guy ask why we aren't selling this yet. It's a pretty nice comment. So as for our next steps, if we were going to go straight to the customer, this electrical design would be implemented into our pool cover design just because of functionality and the ability to cover a larger surface area. But it's actually not. It's actually going to Aaron Pfeiffer next year, and he's carrying this on as his capstone, and he's going to talk to you a little bit about some of the ideas he has to improve this.
So for next year, I would like to add additional sensors for humidity and getting it to work for better conditions. And I would like to do a pool cover mechanical device for a row of plants, to cover a row of plants. And I would also like to solar power and getting that to work with the motor and charging.
So some improvements like we noticed, like first off the bat, was our sensors, and that really was, I mean, it was kind of our fault, but when we ordered them, they were labeled as linear Hall effect sensors, but then as we were trying to get them to work and we were reading the spec sheet, it says in the spec sheet that they're just a latch, they're not actually a sensor. Questions?
This is more a question for Dr. Jalali. If this is going to be Aaron's project for next year, would it be possible to hand that over to mechanical engineering and design it so that there's not so much torque on that motor, maybe a better mechanical design so that they can then bring it back and he and his team can do the electrical work too.
That will be one option. The other option is inviting mechanical engineering students to join you, and I can facilitate that through the program and ask them if they are interested in engagement.
You're applying the torque at exactly the worst place, which is at the very bottom of the arm.
Yeah.
You're trying to turn it this way.
Yeah.
You need to be up here.
Yeah,
applying it.
that's why he also wants to switch to the pool cover where the motor's up top and it's just like a curtain going across the top.
Yeah, it'd be on like a pulley system.
You can worry about the
instead, something
electrical.
like this.
Yeah.
Or
Yeah.
the sensors and all.
Yeah.
Let mechanical engineering figure out how to actually make the mechanics retract and so on without putting so much strain on them.
Yeah, we felt we spent a lot more time on the mechanical problems than we should have been like, we would have liked to focus more of our budget and such on, electric systems.
Well, there's probably at least 2 or 3 other groups that have that same.
Yeah,
issue.
yeah. That's why Aaron gets lucky, because he gets to focus more on the electrical side of this, hopefully. Can build more on top of our design.